somewhere. I would like to bring frequency modulation here. Students. Some.
Так, мы сегодня тоже учились сверху. Как назывался этот объект?
Электроэнергетический.
Ну, в то время у нас было образование на каком языке?
Латышский, да. Латышская группа. Латышский. No one. More to the graph of signals.
the cut of signals. I will have problem. What kind of problem? Now I would like to take frequency modulated signals, but because I need to deal with high frequencies, I have only generator starting from some 20 megahertz. I'll do one trick. I will help my scope. I will use this nice receiver to transfer our researched signal to lower frequency. I will use entering frequency of this receiver for my scope to... My scope will take signal from the entering frequency channel of receiver.
What should I do?
Nothing, watch.
No, I mean, we told.
No.
We don't.
I thought what my scope needs help. Not I, but my scope needs help. Because it's unable to operate, it's unable to perform discrete time Fourier transform on 30 megahertz with resolution required. I'll do trick. This receiver will help. It will transfer spectrum of signal to lower frequency. Okay, all right. Spectrum. Wait 1 second. Am I down? Where is my wire? I just had it in my hand. Signal. Okay.
Did you turn it on radio?
Sorry?
Did you turn it on the radio? Is that radio? I mean?
Yes, it's a sound of radio. I need to just to test my setup. It's external. Set 0, set to 1, okay. Input just for testing. Just for testing, I have input of modulated signal with oh, what I have here. Okay, fine. Simple test, input of modulated signal, 32 megahertz, modulated with 1 kilohertz. And supplied to receiver, I took interim frequency signal at 4 megahertz. And it's for scope. Now, spectrum. Oh. 1 kilohertz modulation. And what about come here, my beauty. this. Okay, here it is with resolution 5 kilohertz per unit. Unmodulated signal, amplitude modulated with 1 kilohertz. Everything we can expect.
Someone online.
Everything we can expect. My demo set is okay. Next. Where we are, what we are talking about. Now, next. Next part of modulated signals. We saw amplitude modulated signal. Here. When the amplitude of carrier is subjected to the law or changes according to the law of transfer to modulated or modulating signal. Our information we're sending. What else we can change? We can manipulate with beginning angle or zero angle and frequency. If you have something like max cosine omega 0 plus phi 0, if you use frequency, it will be frequency modulation. If you change angle, starting angle, it will be angular modulation or phase modulation. You can use frequency or P0 to, how to say, embed your info into carrier. So, we have carriers, cosine omega 0 time plus phi 0. And our S naught A, our signal we would like to send to someone. Urbi and Orbi. We would like to get someone know what new pope is elected. How it will appear? We will see. O max cosine omega 0 time, it's our carrier, plus some factor, depth of modulation, where K is the index or depth of modulation. This part is in radian. It's an instant angle or instant phase. So instant phase is omega 0 time plus Ks time. We can introduce idea or definition of instant frequency. Instant frequency here instant frequency is a derivative from instant phase. It's definitely what it will have. Constant part, frequency of carrier, plus K plus derivative of transferred signal. So instant frequency changes as with the speed of transferred signal. And for those who ignored mass course, we can also write instant phase is from minus infinity to time of instant frequency or integral from 0 to time of instant frequency in time plus angle at the point when transmission starts. It's when we pack our information in angle. We can use frequency to pack our information in. So, in such case, it will be frequency modulation. Instant frequency will be some omega 0, frequency of unmodulated carrier, plus some depth index, our signal. Here, instant phase will be omega 0 time plus integrating from minus infinity to time our signal. I can write FM, it's FM signal, voltage as O max cosine of omega 0 time plus K 0 to time s naught time plus phi 0. Here we see interesting moment. With small depth of modulation and slowly changing signal, there is no difference between phase and frequency modulation. They look very similar. We should introduce one definition. It's a frequency deviation. Idea: maximum difference of frequency where its transferred signal is maximum, frequency goes up. When it's minimal, frequency goes down. So this difference are deviation. For symmetrical signals they will be equal, but deviation means how deep changes frequency, or it's how to say, our usage of frequency channel. Okay. Let's try to understand spectrum of such signal. Let's say we have phase modulation. Our signal will produce is some kind of beta sinus omega st. Beta is an index of modulation, and omega I think like this, single frequency signal. We have signal like cosine omega st. Very simple signal. Full phase of my signal will be omega 0 time plus beta sinus omega st. And modulated signal will look like O max cosine omega 0 time plus beta sinus omega s time. Instant frequency here, what can be found as a derivative of instant phase, will be omega 0 plus beta omega s cosine omega st. So in both instant phase and instant frequency will be subject to harmonic law of change. They will change harmonically. It's unmodulated. Signal. So they both change instantly, change by harmonic law, and index we can easily write modulation index is frequency deviation will be beta omega s, or beta can be written as a frequency deviation divided by omega s. Difference between frequency and angular modulation will appear only when it will appear when frequency of modulating signal, when omega is changed. In case of angular modulation, frequency deviation is proportional to shift of the omega s, and beta is independent. In case we deal with frequency modulation, deviation will be constant, but index will change. Okay, now spectrum. What about spectrum? Okay, one more. Angular modulation. Beta constant. Deviation is beta omega s. Frequency modulation. Beta is deviation divided by omega s, but itself deviation is constant. Now, we have, let's say, PM, and our modulating signal has only one frequency, omega s. In this case, what can I write? I can write its equation S maximum cosine beta sinus omega st cosine omega nu 0 time minus sine beta sine omega st sine omega 0 time. Here I can rewrite for PM equation in this form. It's not handy, it's complex. But to get idea, we can assume small bets. If we assume bets much smaller than 1, meaning narrow band, we have a narrow band modulation. If we have quite narrow band, it is not a huge crime so for narrow band signal, cosine of beta sine omega st can be approximated as 1, and sine of beta sine omega st can be approximately substituted with beta sine omega 0 because of very small deviation. us to write approximate, okay, it's approximate, it's true for narrow band modulation, but, okay, I can write it approximate for max cosine omega 0 time plus beta by half cosine omega 0 plus omega s time minus beta by half. Here will be cosine omega 0 minus omega s time. Oops, what did I wrote? Something familiar, no? Substitute beta with M capital, and you will see amplitude modulated signal. So in small betas, angular modulation looks like amplitude modulation with one moment. This means it has inversion in one sideband. It has inversion in lower sideband. So it's in small depth, PM signal will look like AM, but it's inverted sideband. Meaning what harmonic, if you invert one of the sideband on harmonic amplitude modulated signal, you will get frequency modulated. Okay. Well, in general, this is true for how to say, for small depth signal. For in more general case, you will need to use kind of decomposition. Sum start from minus infinity to infinity m cosine multiplied by cosine of omega 0 plus omega s. Then here this g from gk are Bessel functions. You will need table of Bessel functions and take them with m equal to your beta. This will give you correct frequency decomposition for your signal. Now, what can I do? Look at nice picture. Hello, Mungan. What a nice picture. What is picture of? 32 megahertz unmodulated, transferred to 4 megahertz and taken to scope and subject to discrete time Fourier transform. Okay, what's this? It's an amplitude modulated signal where signal of 32 megahertz is subjected to amplitude modulation with signal of 1 kilo hertz. I can add with higher harmonics. Something familiar, isn't it? Now, same signal. But it's frequency modulation. No modulation. Very small with tiny depth of modulation. I'm increasing modulation index. Oh. No modulation. Very small index, look like AM signal. I'm increasing index. And double, triple, quadruple, and differential frequencies appear. I'll go deeper. 1 second, I will switch to internal. Here frequency deviation. Why it's not going? small deviation deviation 3 kilohertz. 3 kilohertz at 32 megahertz. I'm increasing deviation, more deviation. Small deviation. I'm increasing depth of modulation. See what happens. I am signal. Frequency modulated signal. One moment, I will show it in different scale. No deviation. It's a single. See this? Suspicious. I see the suspicions. Because if you have a bandpass of 40 kilohertz and your signal reach 75, you'll see kind of amplitude modulation, no deviation at what's up? Zero is zero. come here. Okay. What's going on? What's wrong? Okay. You come here. I want you. Oh. And please remain on screen. Yeah. Zero deviation. Come here. Come here. Small deviation. I'm increasing. Nothing. It becomes wider and wider. See, it goes wider and three zero. Very small. $15 kilohertz. Just for comparison, one moment. Deviation 3 kilohertz. Deviation 6 kilohertz. Wait a second. Scope needs time to calculate. Here, deviation 6 kilohertz. Deviation 12 kilohertz. Up. Come on, where are you? Hey, that is mine. Oh, come here. Come here, I'm missing you. For comparison, I'm encouraged now. Kilohertz. At this point, 50 kilohertz. And this one, 75. Six kilohertz. You see what happens? It's like something like this. It goes wider and central part lower. Central frequency if in amplitude modulation center of frequency stands, here it disappears and spectrum becomes wider and wider. And this is single. This what you see is a single frequency. Grizzly party, what are you doing? I'm analyzing frequency modulated signal. And now let's try to take small deviation. Deviation, very. Yeah. Can I please switch to external? Oh, too much. One kilohertz modulating the 2 megahertz. For comparison, amplitude modulated. Yeah. 1 kilohertz modulates 32 megahertz. Let's add what happens if modulation depth increases. Amplitude modulated, frequency modulated. Small modulation then. Increases. Now, let's add higher frequency component. I'm adding third harmonic. Only base frequency with addition of third harmonic. Base frequency decrease modulation then. Maybe this way. Here, very narrow modulation. Addition of third monofrequency signal. You see disappearance. Unmodulated with small modulation depth. Central frequency disappeared. Now it's mono. If I add third harmonic, here it's addition. Only base frequency. One moment, they calculate. Third harmonic added. Fifth harmonic. Unmodulated, very small index. And here receive elements of third harmonic. Here third harmonic emerges. With the high index of modulation, you see central goes down. These are bass and double bass. adding third harmonic, who settles them. So FM signal is quite complex. It contains not only base frequency and side frequency, but also interchange. But this is toy. I can show you a real signal. FM is often used for broadcasting because of its quality. It ensures high quality. It's much harder to change signal frequency comparing to signal magnitude. Okay, let's try to find something. Oh, I think this will be fine. Okay, I'll go here to the modulated. I can get not every station is broadcasting quality signal. Okay. So, here I have something broadcasted from the air. And let's do some small investigation. Let's scan by frequency. Oh, 7, 8, 15 kilohertz. Appears to be sound range, this part. Okay. This part appears to be sound frequency. But we see something high here. Should be, yeah, 19 kilohertz. Come on, wake up. I got a radio signal for you. This part starting. It's a sound, it's a mono, it's a question how to transfer two signals at once. If you need stereo, you need channel left and channel right, yes? How to get left and right simultaneously on one frequency? Here's the answer. This part is left plus right. Oh, here it is. This starting part is left plus right. It's limited, its end somewhere here, around 12 kilohertz. It's a mono signal sound. How to get, but we need, if we transfer left plus right, we need left minus right to get stereo decoded. Let's go to see frequency 3.8 here. Oh, here is my 3.8. You see what periodically around 3.8 appears something like this, like a bridge. So like, it's a balance modulated left minus right. In initial idea, scope needs some time to recalculate, but yeah. Near my vertical red line. See, something goes around. Appears and disappears, appears and disappears. In initial system, at 38 kilohertz, where carrier and left minus right, here at this part, left plus right is transferred. At 38 kilohertz was left minus right. This 48 kilohertz was selected as a second harmonic of the TV signal, but it do not work worldwide because only few countries have fixed this frequency. So engineers of Zenit company decided to do what? Decided to switch to balance modulation. You see, there is no central carrier. All kind around my vertical cursor, but no central. Because carrier is suppressed to avoid interference with TV set. But to recreate signal, local oscillator, balance modulation, SSB, do what you want, but you need to recreate central frequency. To do so, this thing is added. See why? 19 kilohertz. It's so-called pilot tone. Broadcasted signal contains so-called pilot tone. It's a reference frequency for local oscillator to recreate, for this baby, it's central frequency. This allows to decode left minus right signal. This part is complex stereo signal. And how do you think, what is this? See? Something happens, it should be this one is a second harmonic of pivot tone, and next one it will be third harmonic of pivot tone. Third? Yeah, third. Something happens there. It's an RDS signal. When you switch your radio, car radio, you see name of station and song broadcasted. Here this info. Where my cursor stands, it's a signal RDS. It also can be used to transfer emergency information. It has an open part for public and a special part for it's for rescuers. Yeah, they can be. I'm not sure. No, this station do not broadcast. Can be also. In early days it was called a Microsoft Broadcasting System. One more data channel to broadcast business info. But here, L plus right, pivot tone, left minus right, this balance modulation should be recreated with the central oscillator should be adjusted with the second harmonic of pivot tone. And this part, it's an RDS digital signal. Name, song play, may contain some business info, and so on. This real spectrum from the air. Bit more complex. And it's demodulated. Before the modulation, here is spectrum before it's demodulated. Nothing. Nothing is clear here. Okay, you saw it. Wow. The advertisement numbers. No. Thank you, guys. But no. Okay, I don't see anybody on the line. Maybe some questions.